Hello everybody, my name is Jonás Chaves-Montero and I am a postdoc at the High Energy Physics Institute in Barcelona. I'm going to talk about ForestFlow, that is a new emulator of the Lyman-α forest that makes precise predictions from linear to highly nonlinear scales. This is a project of the DESI Lyman-α working group, and the main authors are myself, Laura Caballero Garcia, Martin Logan, and Lya Rivera. So let's start with a brief introduction. Lyman-α forest refers to absorption lines in the spectra of high-redshift quasars resulting from Lyman-α absorption but neutral hydrogen in the intergalactic medium. The main advantage of this observable is that it allows us to access higher redshifts than those proved by galaxy clustering or with gravitational lensing. In order to predict the Lyman-α forest clustering, there are two main approaches. The first one is based on cosmic perturbation theory. This makes very robust predictions from linear to quasi-linear scales, but at the cost of marginalizing over many free parameters. On the other hand, we have emulators that make precise predictions from quasi-linear to non-linear scales, but at the cost of running many cosmological hydrodynamical simulations. And we can see here one example of how these simulations work. We first run the hydrodynamical simulation, then we put a quasar, like a line through the simulation, and this line travel through the intergalactic medium and the light get absorbed by the different overdensities of the ultra hydrogen, and you get this profile here. So we are going to focus now on this strategy of emulating the Lyman-α forest. And most cosmological emulators of the Lyman-α forest or galaxy clustering or with gravitational lensing or so on predict summary statistics as a set of R beams or K beams. The main limitation of these emulators is that you need very big simulations in order to access large scales. And on top of that, if you want to resolve a small scale, you need very high resolution. So big simulations, high resolution, takes a lot of time. For Lyman-α forest, we need to access very large scales for bioanalysis and small scales for the one-dimensional power spectral analysis. So that will mean a suite of cosmological hydrodynamical simulations, each of them with at least 3 gigaparsec per side, and that's unfeasible right now. The other point that is important for the Lyman-α forest is that when you make an emulator for a particular summary statistic, if you want to derive another summary statistic from this one, for example, from the 3-dimensional power spectrum, derive the 1-dimensional power spectrum by integrating perpendicular modes, in traditional emulators, you need to extrapolate and interpolate, but reduce a lot the predictions of this derived statistic. In order to mitigate the impact of these different limitations, we have an novel approach, that is emulate the coefficients of a parametric model instead of the summary statistic at a set of beams. What we emulate exactly is the two Lyman-α linear biases that set completely the large-scale behavior of the 3-dimensional power spectrum and 5 parameters capturing small-scale variations of this statistic from linear theory. And you can see this here in the first equation. We have the two linear bias parameters, bias delta and bias eta, and this set this large-scale behavior because by combining this with a linear power spectrum that comes from a Boltzmann solver, we can get precise prediction for the 3-dimensional power spectrum on arbitrarily large scales. And on a small scale, we have a correction that accounts from nonlinear growth, small-scale velocities, thermal broadening, and gas pressure that modifies this expression. And we emulate the 3 parameters of this expression, these 7 parameters. Related to what I was talking about before about this other statistic that we can derive from a particular statistic, the idea is that we emulate these parameters, we predict the 3-dimensional power spectrum, and by taking the Fourier transform, we get the 2-point correlation function that it is used in BEO and Alpha-Paczynski analysis of the Lyman-α forest, We integrate the perpendicular modes to get the one-dimensional power spectrum that it is used in a small-scale analysis, for example, to get the neutrino mass or the amplitude and slope of the power spectrum on the scales. We can also integrate the perpendicular modes in a different way to get the cross spectrum. That is an attempt to do a full shape analysis of the Lyman-α power clustering. So let's present the emulator ForestFlow. It is based on conditional normalizing flows. So you get what we predict, as I said before, is the parameters of this P3D model. And we make these predictions a function of 6 parameters capturing the cosmological and IgM dependence of the Lyman-α forest. I don't want to go into details, but the main point of using a conditional normalizing flow is that we get not only the value of the parameters of this P3D model, but also the correlation between them. And then we can propagate these values and correlations to get predictions from the summary statistics and errors. That is very important. So the input data that we use for training the emulator, these are the best fitting parameters of the model that I saw before to one-dimensional and three-dimensional power spectrum measurements from a suite of cosmological and dynamical simulation. These are 30 simulations of 67.5 megaparsec per site. These simulations are small, and I said before we want to measure the alpha linear biases that set the large-scale behavior of the power spectrum. So we have to pay a special care in order to reduce the impact of cosmic variance on the training set. In order to do that, we use fixed sample simulations that, if you're not familiar with this technique, the main idea is to reduce a lot cosmic variance on very large scales by changing the initial conditions of the simulation. We take the average of the measurements through the 3 simulation axes to further reduce cosmic variance to carry out a joint fit of the parameters that I was talking about before of this model using different snapshots from the simulations, the 11 one that we have access between Redshift 2 and Redshift 4.5. And finally, we evaluate the model, this three-dimensional model with this parameter, using exactly the same K-modes that we measure from the simulation. So we know that we can compare exactly the same things and we don't have problems due to the limited number of modes, for example, that we have from large scales. And what I'm showing here in this plot is the ratio of the three-dimensional power spectrum and the linear power spectrum as function of the scale. The dots are the measurements from the simulation, and the solid line is the best fitting model. As you can see, it's doing a great work capturing the scale dependence of the power spectrum. And in the bottom panel, you can see that we captured the dependence within 10%. And in fact, on large scales, these wiggles that you can see, this is just due to cosmic variance, so we expect that in reality the precision is even better, around 5%. And the dashed lines, what they show is the prediction from the best fitting model, but when we don't take into account these small scale corrections. So as you can see, small scales modify the three-dimensional power spectrum by around small scale correction by around 10% on scales of 0.3. So what the main point of showing this is that all the scales that we are using are affected by non-linearities, but even that the case, because of the way that we fit the model and the way that we take into account and care for cosmic variance, we can measure these large scale Lyman-α biases with very good precision, and we will see later. And the conditional data that we emulate as a function of 4 are 6 parameters, and I said before, only 2 parameters capturing the cosmological dependence. This is very important. Only the amplitude and the slope of the linear power spectrum on small scales. It works because for the redshift of the Lyman-α forest, the universe is almost Einstein-de-Sitter. That means that it is matter-dominated, so the redshift distortions, the growth history, and the expansion histories are almost the same independently of the cosmological parameters. And for the IgM physics, we use different parameters that allow us to capture different, for example, the impact of pressure, the thermal broadening, and so on. related to using only these two parameters, the parameterization for the cosmological dependence, despite our strict simulations only vary the primordial power spectrum, the amplitude and the slope, we will see that our emulator delivers precise predictions for any combination of lambda quantum matter parameters, two lambda quantum matter extensions, machine neutrinos and curvature, and ionization and thermal histories not included in the training set. So as for the prediction of the model of ForestFlow now, the results for the parameters that we emulate. What we find is that for the Lyman-α linear biases, the prediction goes from 1 to 4%, and when we propagate that for the large-scale behavior of the three-dimensional power spectrum, we get from 1.8 to 2.8 precision, predicting the three-dimensional power spectrum along the perpendicular and parallel directions. And the main limiting factor here is not the precision of the emulator, but cosmic variance that affect our training set because of the limited size of our simulations. And the precision of the model predicting other parameters, these small scale corrections, is around 20%. But in the end, this is not very informative for the prediction predicting the three-dimensional power and one-dimensional power spectrum from intermediate to small scales. So it is better just to go to the prediction from this of the parameters from ForestFlow, evaluate the different expressions, and get prediction from these summary statistics. As you can see here in the left panel and the right panel, these are the three-dimensional power spectrum, the one-dimensional power spectrum, predicted from ForestFlow, solid lines, and measured from the simulation in the dotted lines. And the prediction for the three-dimensional power spectrum around 10%, and the one-dimensional power spectrum 1%. And this is impressive because even K-beams emulators designed directly just to predict the one-dimensional power spectrum, they get more or less the same level of precision. Even though this emulator is also predicting the three-dimensional power spectrum with very good precision. But this is just at the center of the parameter space. So doing a leap one out test, what it means is that we remove one simulation from the training set, we train the emulator again, and we use the simulation for predicting the precision of the emulator. And we do this again over and over for all the different 30 fixed sample simulations that we have in the training data. And what we are showing here is the average of the precision for different redshifts. As you can see, it is more or less the same, around 10% for the three-dimensional power spectrum, from quasi-linear to nonlinear scales. Remember that on linear scales, we get around 2% precision. And for the one-dimensional power spectrum, this from 1 to 2% precision, depending on the redshift. And as I said before, the emulator also works for other cosmologies that are not in the training set. For example, this growth simulation that we are showing here uses a different value of omega matter and the Hubble parameter, and the precision is the same. This simulation has massive neutrinos, and neutrino, I think, is 0.3 electron volts, so already ruled out by the data. Curvature, also a very large value, and also great precisions, and the ionization histories that are not in the training set. And thanks to the parameterization of the eigen dependence, we can also get very good results here. It is really interesting that we get even better results than the K-beam emulators for this simulation. Some of the applications, the novel applications of this emulator, because again, we can make consistent predictions from large to small scales, and this is something new. And for example, we can use now priors from one-dimensional analysis, from a small scale analysis, on large scale analysis, for example, VEO studies, and in that way increase the precision measuring VEOs. Or, for example, extend a Kompachitsky test from linear to quasi-linear scales, or even nonlinear scales, or a full shape analysis of the three-dimensional power spectrum. And finally, the summary is that we have designed this emulator, ForestFlow, that is bridging the gap between large scale and small scale Lyman-α clustering studies. It emulates the two Lyman-α linear biases that set the large scale behavior of the three-dimensional power spectrum, and 5 parameters capturing small scale deviations from linear theory. And it makes this prediction as a function of cosmology and ideal physics. The precision of the model is from 2 to 3% on linear scales for the three-dimensional power spectrum, and around 10% from quasi-linear to nonlinear scales, and for the one-dimensional power spectrum are around from 1 to 2% across the full range of scales of interest for DESI. In addition, it is important to say again that the emulator also makes precise predictions for cosmologies that are not in the training set, including non-color matter extensions like massive neutrinos and curvature. Next slide.